Bismillahirrahmanirrahim. Assalamu alaikum viewers. Welcome to my channel, and in today's video, as you can see the heading, we are going to discuss the first fundamental theorem of calculus, which actually explains the relationship between your differential and integral calculus. So before commencing this theorem, before trying to understand this theorem, I need to discuss here that the concept of definite integral was already presented by ancient Greeks, especially or principally Archimedes, near about 2000 years ago. Okay, so, and but it wasn't that much clear how it was presented by Sir Isaac Newton and Sir Leibniz, who were independently but simultaneously they were working in the field of calculus, and they presented the concept of derivatives quite exhaustively. So over there, these two men in 17th century, they explained how to measure the area under the curves or the set of curves by applying your antiderivatives, or how to evaluate the definite integrals. So this thing gave rise to the two major fundamental theorems of calculus that we are going to discuss over here, the very first one. So over there, we will try to understand the fundamental theorem of calculus by considering a definite integral of function f in such a way that we are going to take a variable in the upper limit of the integral. Why we are taking, we'll just try to understand that thing as well. So before moving to the corresponding definite integral having a variable in its upper limit, just try to understand that if we are having a certain function f, no matter you can express this function with respect to any variable you want. I just say that let it be your f of t, for example, and it is bounded by two values on the x-axis, a and b dt. Then if I just try to figure out or try to understand this thing geometrically, I just say that if I just try to plot this, I'm having t-axis on the horizontal one, and on the y-axis I'm going to take the readings of your function of t. If I try to plot this function graph, it appears, for example, a curve. It gives me a curve something like this, and I just bound this curve by two values, t is equals to a and t is equals to b. Okay, I just try to represent these lines, t is equals to a and t is equals to b over here. So the area which is bounded by this curve, this line t or axis t, the line t is equals to a and t is equals to b, the answer that you are going to get it exactly in a number form. You're going to have some constant answer. Okay, in a number form you're going to get the answer. But over here, instead of taking this, if I just say that and one thing more I just forgot to mention here, that in one of my previous videos in which I try to explain the geometrical interpretation of a single variable function or a univariate function, over there I try to explain it by means of a Riemann sum. The description of the link of that video is mentioned in the description box, you can see over there, and also the explanation of the tangent line and derivatives, you can see the corresponding video link over in the description box as well. So both those videos are really going to help you a lot in understanding the first fundamental theorem of calculus. So you see, we just take the help of the Riemann sum in finding out the area under the curve. Now, instead of taking a number value b over here, if I just say that if a function is continuous in a closed interval AB, then definitely it is going to be integrable on the same closed interval A and B. And that's what we have discussed in the previous video, geometrical interpretation of univariate functions. So we are just picking up that theorem or that explanation, and we just say that if there is a certain value x is any number present between a and b within this closed interval where your f is entirely continuous, I just say let your x is over here. Then if x belongs to this closed interval AB such that your f of t is continuous, so definitely it is going to be integrable. So I just say that if your f is continuous at this point as well, then it is definitely going to be integrable. And the reason of taking the variable t for the function f is just to make a distinction, because over here I'm using a different variable x. So if I take same x over here, it is going to cause confusion. So you can take any variable to represent your original function f. There's no restriction if you are taking the upper limit in the form of some other variable. Don't take both variables same. All right, so this is it. So you are having a stuff like this. So once if you are having a definite integral having a variable in the upper limit, you are going to have some answer representing the area, but it is not going to be exactly in number form. It is going to be having it is going to appear in the form of some equation involving x. So we are going to represent that equation as our f of x. All right, like this. So you see this function f of x that we are going to obtain after evaluating this integrand with respect to these two limits. This function is going to express the measure of the area under this curve f of t and your t-axis and this line t is equals to a and the line t is equals to x. Okay, so this function f of x is going to explain here the measure of the area bounded by this curve, this t-axis, this line t is equals to a, and this line t is equals to x. So it's going to explain you the area. That is not in the number form. Okay, fine. Now let us put down here then this notion is going to give rise to the first fundamental theorem of calculus. So first of all, we are going to pick up an example and we'll try to figure out this concept over there, and with the help of that we are going to put down the statement of this first fundamental theorem of calculus. Okay, so and before putting down the example, I must say that if we are having this function capital F of x, which is explaining the integral of this function f of t, and if I just take the derivative, of this function f of x with respect to x, like this, then it is going to give me the same function f back in the form of f of x. Okay, that's what this theorem is all about, and that's how it is relating the integral calculus with the differential calculus. So let us start and try to understand this theorem by means of an example here. So here you go, an example. Let me write it down. So here you go, an example, f of t is equals to t squared. So if I just try to plot, and over here I just we just said that your f of x is expressed as the integral from 0 to x f of t dt. All right, so you can say that it is 0 to x, and f of t is your t squared up to dt. All right, so now what is going to be the value of exact b? We have got no concern with it. Okay, and we just say that your x is actually belong to this closed interval 0 and b is any number. We have got no concern with it. Okay, so over here, I have just tried to maintain a graph of your f is equals to t squared. This is your graph, all right? And I just assume that your b is somewhere on the t positive t axis, and your x is lying between 0 and b. So I just said that let your x is lying somewhere here. For instance, just for example, I just say that your x is lying over here. Okay, and I'm going to draw here line t is equals to x, which is right parallel to your y-axis, and let me try to draw it out over here. Okay, so here you go. So you see the area bounded under this curve, this line t is equals to x, the t-axis from 0 to x. So this is actually the area that we are so dealing with, and this f of x is going to explain the measure of this area that I have just shaded over here. Okay, but it's not going to give me exact answer in numbers. It's going to give me a corresponding equation, all right? And that's what we have expressed as f of x, the function of x. That is going to be an equation with respect to x, so obviously it is some kind of function. So that's it, that's how it is expressed. So how we are going to evaluate this definite integral, which is having variable in its upper limit? So as I've explained in my previous video, geometrical interpretation, you can see the link, I repeat once again, in the description box. So there we have explained quite exhaustively that we are going to divide this entire region, this entire area, shaded area, into infinite number of rectangles. Okay, and we are going to keep those the width of those rectangles as small as we can in order to gain perfection, and in order to get when we sum up the area of all those infinite rectangles, then we are going to get the sum of that, all those areas are going to interpret exactly the value of this area bounded under this entire curve, the shaded region. So for understanding, I just try to draw here a rectangle, for example. Okay, though this rectangle is quite broad, but just for understanding, I have just drawn a rectangle here like this. It appears something like this. Okay, so in this way we are going to have a infinite number of rectangles. So once, if the rectangle numbers are too many that you cannot even count, so how much thin their width is going to be. So once they are getting thin, so this extra region is which is causing error, which is going to cause error, is going to be minimized. So we are not going to move in drawing such infinite number of rectangles. We are just going to take an idea, and we are drawing a width, a sufficiently broad rectangle here. And I just name I'm just considering this rectangle over here right now, and I just say that it starts from this point, ends at this point, and I am going to name this end point of this rectangle as my, for example, WI. Okay, this second rectangle is going to be W2, but I'm just trying to generalize it, so I'm taking it WI. All right, so if this is the value of your x, then the corresponding value on the y-axis is going to explain here f of wi. Am I right? This is it. And over here the graph tells that this wi is actually 2. So how you're going to interpret this wi? So you see that this is actually your second rectangle, and it is having a width 1 unit. All right, so I'm going to explain this width as my del t. All right, the width from here to here, I'm going to explain it as my del t. All right, so and it is the triangle number 2, and so that's why it can be expressed as number 2 triangle getting multiplied with del t, and del t is this is W2. So del t value is 1 because its value is 1 unit, so it is going to be 1. So that's how I'm getting 2 here. So from the origin, the value of your wi is 2 here, and it's the second rectangle, so the width of the second rectangle is w2. So how about if I talk about my ith rectangle? The corresponding wi is going to be, it's the ith number rectangle, so it is going to be I into del t. All right, this is it. So as we have, just keep this thing in mind, and let's move on over here. So you see, according to the Riemann sum, your f of x can be determined by drawing such infinite number of rectangles, such that n is representing number of rectangles, and it is approaching to your infinity. Then it's too difficult to draw the summation like this. Okay, so I is going from 1 to n, and you are going to sum up the area of all those infinite rectangles, the thin rectangles. So here the length of the rectangle is representing f of wi, and the width of the rectangle is represented by del t. So all of the rectangle areas you're going to sum from I to n, and n is moving to infinity like this. Okay, it is something like this. All right, so if we just try to erase out this at the place of my wi, I can write I into del t. All right, so it is going to appear something. I is going from 1 to n, and I can write it like this: f of I into del t. Okay, I'm not writing I in the subscript just to avoid complication. All right, so now you see your f of t is t squared, so f of I into del t is going to be I del t whole square. Okay, so now we just keep on moving following the limit concepts, and it is going to be I del t whole square into del t. Okay, so this is going to be limit n is approaching to infinity. I is going from 1 to n, I square, and this is del square, and one more del t, it becomes del t cube. All right, this is it. Now, one thing. Now you see the limitation or the boundary where your rectangles are going to stop is this. Okay, you have to draw, you are going to draw your rectangles, keep on moving, and you are going to stop. This is going to be the line of your last rectangle, right? So you see, if you try to find out the value of your del t, how you're going to evaluate, you see the entire the entire length of the t-axis, which is involved in this area region, is starting from 0 to x, so it is entirely x. Okay, so if you divide your this length with n number of rectangles, you're going to get the width of the rectangle, right? So you see, the width of the rectangle can be determined by dividing this length with the total number of rectangles, so individual length can be determined in this way. So at the place of your del t, how about if you just write x upon n, so it makes sense. So I is going from 1 to n, I square, and it's x upon n whole square. All right, this is it. I'm sorry, it's cube here, sorry. So just like this. So you see the summation over here is representing just I. So x and n are constant numbers here. You're going to write it out before the limit. Okay, so it's going to be x cube upon n cube. I square. All right, this is it. Now you are going to use here the formula of your summation n square. It is a complete derivation in limits. People of pre-calculus are very much acquainted with that, and and is this the formula of your limit. Phi is going from 1 to n, and limit n is approaching to infinity, and if you're having I squared, it is going to be replaced by, like, if I just try to interpret it in this way, it is starting from the summation of I squared, and I is going from 1 to n, and n is infinity. So the summation of the square of the numbers, like this, okay? And it is a derivation that this series of the squares of the natural numbers, no matter where it is ending, it is equivalent to this relationship. All right, so we are going to replace this thing with this over here. All right, so let us continue in the next line. So this thing is going to be x cubed upon n cubed, and it is going to be replaced by this stuff. Limit n is approaching to infinity, and the summation of this thing is equal to this, n times n plus 1, 2n plus 1 upon 6. Alright, let us bring this n cubed inside and write it after the limits in order to solve this thing. It is x cubed, limit n is approaching to infinity, 1 upon n cubed, n plus 1, 2n plus 1 upon 6. Alright, so now let us try to handle this thing with respect to the powers. So if we directly apply the limit, it's going to cause confusion here. So if we just multiply these three factors in the numerator, then it is going to be helped out. It is going to be, if I simply cancel out this thing with 1n with 1n, I'm simply having n plus 1 and 2n plus 1 upon 6n squared. Okay, let us multiply this thing. Let's see what we have here. N times 2n plus 1 plus 1 times 2n plus 1. It's trying to be a bit exhaustive, and this is it. So limit n is approaching to infinity, 2n squared plus n plus 2n plus 1 upon 6n squared. All right. So how about if I just write down my 6 outside? It's a constant number. So limit n is approaching to infinity, and it's going to be 2n squared plus 3n plus 1 upon n squared. All right, so now let us now take a back substitution and divide all these three terms with your n squared. So x cubed upon 6, and after that we are going to apply the limit. It's going to be 2 plus 3 upon n plus 1 upon n squared. All right, now once when we apply the limit, so once when we just apply the limit, it's going to be x cubed upon 6 into 2 plus 3 upon infinity plus 1 upon infinity squared is infinity, and no need to write power on the infinity. So these two terms will turn into 0. So what you're having here is x cubed upon 6 into 2, and in cancellation you're having x cubed upon 3, and this is the function f of x of this representing the integral, the definite integral of of this function f of t having these two limits. So this equation x cubed upon 3 is representing the measure of the area bounded by this curve, this line t is equals to x, and this t-axis from 0 to the x. Okay, so this shaded region is expressed by means of this equation. All right, and this is in the equation form. It is not exactly a number, so that's why it is behaving as another function that we represent as our capital f of x. Okay, this is the first part of your fundamental theorem. Move to the next part. How about if we just take the derivative of this function? Okay, so this was the definite integral of your f of t. Now let us take out the derivative of this function. So let me use a different page. It's completely exhausted. So this is it. So once when you take the derivative of this function with respect to the given variable, you just differentiate both sides with respect to your x gently, and the derivative through first principle method and through implicit methods, the videos are there. You can see them in the description box. So once when you apply here the derivative of your xn, you just take that concept. So it is going to be nxn minus 1 upon 3. So this and this gets cancelled. You're having x squared, and this is your f of x, which was similar to your t squared. If you replace your variable x by your t, you're having t squared, and so on. So you are having the same function back that we were discussing in the beginning. So this is what your first fundamental theorem of calculus says. So let me write down the statement for you here. It says that let a function f be continuous on the closed interval ab, and let x be any number in the closed interval ab, and if f, capital F, is a function defined by this behavior, then the derivative of this function f of x is going to give you this function small f back. Or equivalently, you can state it like this. So you see, you can also understand it in a way that this differential operator is cancelling out the effect of this elongated sum, the integral s, and you're having the same function restored. Nothing is going to happen to it. So that's what is happening in your first fundamental theorem of calculus, and how beautifully it has maintained an axis between your differential and integral calculus. And the example that I have just maintained in the beginning is just an example. There are several dozens of examples, numerous examples that can satisfy. So you can pick up any function you want, you can assign any interval you want, you can take x in the middle of that interval and use that thing. So that's how we just maintain this theorem. And then this theorem provides us a shortcut in finding out the exact function whose integral function if it is given to us. So that's all for today. Inshallah, in the next video we are going to move to the next or the second fundamental theorem of calculus in a short course of time. So till that period, take good care of yourself and study well. And if you find this video helpful, I'll be very grateful if you subscribe my channel and hit on the like, and share this video as much as you can with your other friends and learners who are interested. And don't forget to put down your feedback in the comment box below. So take good care of yourself, and see you in future as soon as possible. Okay, Allah Hafiz.